Okay, once again, I'm gonna do a lab. I'm gonna collect the data, or at least show you how it's done. This is for determining the speed of sound. You actually can figure out the speed of sound using this kind of tricky, or no, ingenious method. So I've got some tuning forks here, and each of them has a number and a letter. The number corresponds to the frequency of the tuning fork. That's how fast it vibrates. And the letter below, it represents the musical note that that frequency is equated with by a musician or whoever. So this one here, I don't have my glasses on. I believe it's a...
I'd help you out, but I can't quit videoing.
Oh, my videographer. This is a D. So it's 288 hertz. Hertz is the unit. Okay. So these are rather delicate instruments. You don't want to bang them on a table or anything hard. So we have these, I call them bumpers. These green devices, and what you do is you hit it on the bumper, and I can force this table to vibrate at the same frequency. But that's not what we're going to do. I'll show you more of that in another video. If they're vibrating, you don't want to put a vibrating tuning fork down on the table because you're going to mess it up. So you just touch it to a soft portion of your body, never to someone else's ear. That's painful. So, but you don't need all those rules because I'm going to do it. Now, I've got a very interesting contraption here. I've got a graduated cylinder, and in the graduated cylinder, I've filled it with about 2/3 water, 3/4 water, and then I have this PVC pipe or ABS pipe. And an important thing that I'm going to have to do is I'm going to have to measure the inside diameter of the pipe. So I measure from that side to the inside over here, and I'll report what that measurement is. But that's to know the diameter of the tubing, which you'll see later as a part of your calculation to determine the wave speed of the sound. Anyway, whoa, this is such a complex lab. If you're really doing this lab, this would be a formal lab. And I'm still debating about whether I'm going to have you do it as a formal lab, but enough talk. What's going to happen is I'm going to start this tuning fork vibrating, and I'm going to hold it about a centimeter above the opening of the tubing. When I do that, the sound waves are going to go down the tubing until they hit the water, which is right here, okay? And in that air column, I'm going to move the tubing up and down like this until that frequency resounds. We call it resonance in musicians. We call it resonance. We'll talk about that more later. But it's basically a resounding of the vibration. And what I mean by that, you looked at standing waves last week in homework. So when a wave goes down and gets reflected back up, if the crests and the nodes meet in exactly the same spot, the sound will resound. So it will become louder. Let me just demonstrate. There it does a little bit. There it does more. I'm going to restrike it. Now that I have approximately where that resonance point is, I'm going to change the position of my hand so it's easier for me to do this. You generally would be doing this with a partner, and I don't have a partner right now. Hear that, how it resounds? I'm going to go up a little higher to see if that's the best spot. Yeah, that's pretty much the best spot. One more time. At this point, what I'm going to do is I'm going to stop that from vibrating, and I'm going to take my metric ruler and I'm going to measure from the surface of the water up to the top of the tubing, because I want to know how long that air column is in which the vibration is resounding. Okay, so it looks like, oh, the blessing of not having eyes. It looks like about 28 centimeters. 28.1 centimeters. Okay, so on your lab, you're going to want to write that length of the air column, and in the same row that you write the frequency and the note, the particular letter or note of that frequency. So that's an important thing. That's not, you're going to do some mathematics to figure out the speed of sound. What I'm going to do now is I'm going to take another tuning fork, and I'm going to go through the same process and figure out what point this resonates the most, and on we go. So this tuning fork is, I think I put these in musical order. So that one was
A D.
A D. This one will be a what?
E.
Okay, so for those musicians out there, and the frequency is 320 hertz. This one was 288 hertz. D, and then E. So the frequencies are very mathematical. Notice something else. Notice how the length of the tines of the tuning fork, the E is shorter than the D, and that's because the E has to vibrate more quickly. So the shorter the tines, the faster they can vibrate. We'll talk about that more later too. Okay, so E. Let's go ahead and see where it resonates the most. So a little hint. This frequency is higher than that frequency. So if the frequency is higher, what would you guess about the wavelength? I want you to know that wavelength, and you should have learned this last week in your homework, wavelength and frequency are inversely proportional. As one goes up, the other goes down, and vice versa. So the column of air in the tube in which the sound resounds, if we're a higher frequency, what do you predict? Okay, enough talk. That's resounding a little bit there, but let's see if we can get a louder sound. Another thing that's very tricky about this is, and we haven't looked at standing waves, but you can have different harmonics produced. For those of you musicians, you know what I'm talking about when I say harmonics. But yeah, more later. This is such a cool lab. Ugh. Okay, I'm close. I'm going to change my hand position. It's a pretty nice tone. Okay, so. I love that sound. Alright. Untest Miss Lyle, come on. Okay, so I'm gonna measure the length of the air column from the surface of the water to the top of the tube. And that one, lo and behold, 25.2 centimeters. 25.2 centimeters. So, think about what the last one was. Is it fitting with our understanding of frequency and wavelength relationship? Okay, next one is for you musicians. I bet you can't guess. By the way, I have a friend doing the videoing, and she actually is a music teacher. So she's an accomplished pianist. And yeah, so her name's Miss Colwell. Miss Colwell?
I'm assuming it must be an
No,
F.
exactly.
Yes,
What
and
frequency?
341.3
341.3 hertz.
hertz.
Wow. Okay, so quickly we'll see. By the way, that's a higher frequency. Well, there's a harmonic, but that's not the one we want to find. Okay, I'm going to change my hand position. Okay, I'm gonna settle for that. I'm trying to be careful to reduce the air in case I'm expecting a formal laugh from you. Alright, so 23.8 centimeters. 23.8 centimeters. And the next one, the note will be
G.
a G. Whoa. And the frequency?
384
384
hertz.
That's 384 vibrations, back and forth movements in a second. That is a fast vibration. Wow. 384 hertz. Yeah, there's a harmonic right down there. Okay, I'm gonna change my hand position. Okay, I think that's just about the right spot. Take a measurement of that. And I'm sure you're predicting what you think the measurement will be. Let's see how close you are. 20 point. Wow, 20.65 centimeters. 20.65 centimeters. Okay.
Bet I can guess this one. Is it
Wait. Don't tell me the musical note. Tell me the frequency.
440?
Whoa.
Is it an A?
Whoa, it is an A, but guess
Oh,
what?
it's not 440?
Well,
Too high.
no.
Okay.
We aren't a perfect.
Oh.
We don't have a perfect A.
426.7. Oh,
So why do you
shucks.
say 440?
That's just what all the orchestra's tuned to, an A440. It's above middle C.
Yeah, but that's a perfect day, right?
Oh, I'm sure.
Okay, 426
26?
point what?
I can't remember. 7.
426.
I hope it's 26 and not 28. I can look later.
It's 426.
0.7.
Yep.
Okay.
Okay, choose your hand position. One last time. Okay, I think that's pretty good there. $18.6 centimeters. 18.6 centimeters. Yep. You hear that vibration?
Mm-hmm.
It's causing that.
Don't know.
Okay. Focus on what you're doing. Okay. I'm telling you, this is a B, so what frequency is it?
No idea.
No idea.
480.
480.
Letter B as in boy. 480.
Now, does the song from Sound of Music, doe, a deer, a female deer, does that start with D for doe? Or does it start with C?
I think it depends on what key you're playing it in.
I think that's an extra credit question. Wait. On the movie.
I know. I'm not sure.
Some music teacher you are.
Sorry.
Come
I'm an elementary music teacher. Come on.
on. We won't hold it against you. 'Cause
Good.
You're doing me a favor, a huge favor.
Right.
I'm messing around now. Okay, back to staying on task. One last time. Okay, I think that's pretty good. I hope it's good. Okay, 15 centimeters, 15 point. 15.75. 15.75 centimeters. Wow, that's a lot of tuning forks. In lab, you probably wouldn't have time to do that many, but by doing a lot of tests, what will that most likely cause our results to be? Think back to last semester. More tests. Anyway, I think we need to take a look at the temperature in the room. That's very important. So, Ms. Colwell, come on up and take a video of our thermometer.
Just so you see, it is on Celsius.
Okay, and then before you stop, why don't you take a little video of our tuning forks, kind of come up over here, and that way we can see the size pitch relationship, because I think you teach your students about that, right?
I do.
What is that?
The larger the instrument, the lower it plays. The smaller the instrument, the higher it plays, which should be true for your tuning forks.
So give us an example of a musical instrument.
A trombone or a tuba is big, and it's going to play low. And a violin or a flute, piccolo, smaller, going to play higher.
So how does that relate to humans?
Yeah, that's a good question, because we've seen opera singers like Pavarotti, who's very large, and he sings, yes, and he sings tenor. So he sings a higher male part. So that's a good question. Maybe it has to do with diaphragm, the face, the way the face is constructed. I don't know. That's a good question.
What about the things that vibrate?
Your vocal cords. Ah, that's a really good comment, Miss Lyle.
So what kind of vocal cords, what would the vocal cords have to be like to
Sing.
a high note?
I would think they'd have to move faster and be like smaller.
Come out.
Yeah. Right?
Oh,
Do you
so
think?
like
Do you think?
shorter?
Short. Thank you. I'm sure that's what it is.
And-
And a bass or a low voice would have to, do you think, vibrate slower? I'm guessing.
Well, these tuning forks, huh?
No.
No, I'm just thinking.
Okay.
All right, that's a great thing
All
to
right.
think about in research, if you're into vocalizing, singing, in other words. Okay, so I think that does it for the collecting of all our data. So, have fun with that. Just pay attention, follow the directions, follow the instructions, and you'll have great success.
Okay.
And if you have questions, just email me. All right? Good times.